Cycloaddition reactions are pericyclic reactions in which two pi systems combine to form a single ring structure. Now, there are two different types of cycloaddition reactions. We have cycloaddition reactions that take place under thermal conditions and cycloaddition reactions that take place under photochemical conditions. And let's begin by recalling what a thermal condition is. So a thermal cycloaddition reaction is a cycloaddition reaction in which the energy source is heat. The energy comes from heat. Now, in a thermal reaction, in a thermal cycloaddition reaction, we can generalize the following two important points. If the reactant molecules have a total of 4n pi electrons, where n is simply a number that begins with 0, it could be 1, 2, 3, 4, and so forth. So basically, if we have 0, 4, 8, 12, 16, 20, and so forth pi electrons in our reactant molecules, then the thermal cycloaddition reaction will not take place. There will be no rotation that is possible to basically undergo a concerted one-step mechanism. For example, if we have two ethene molecules reacting under thermal conditions to produce the cyclobutane, no thermal cycloaddition reaction will actually take place because we have 1, 2, 3, 4, we have 4 pi electrons in our system. Because 4 electrons is equal to 4 multiplied by 1, where n is equal to 1. So the above thermal cycloaddition reaction will not take place since the number of pi electrons is equal to 4 equals 4 times 1, where n is equal to 1. However, if the reacting systems have, let's say, 2, 6, 10, 14, 18, 22, and so forth, basically 4n plus 2 pi electrons in our reacting system, then the thermal cycloaddition reaction will take place. And the prototypical example of such a thermal reaction is the Diels-Alder reaction, in which we have our alkene, our dienophile, reacting with our 1,3-butadiene, our diene, under thermal conditions to produce the cyclohexene. So because we have 2, 4, 6, we have 6 pi electrons in our system, and 6 is equal to 4 multiplied by 1 plus 2, so our n is equal to 1. Since this fits our criterion, then we see that the thermal reaction will in fact take place. Now, the exact opposite is true when we are under photochemical conditions. So basically, a photochemical cycloaddition reaction is a reaction where the energy doesn't come from heat, but it comes from light. So basically what happens in photochemical conditions, we have our light that shines onto our molecule, bumping an electron to a higher orbital, and that reverses the results we just discussed. So basically, for photochemical cycloaddition reactions, we see that if we have 4n pi electrons in our system, then our photochemical cycloaddition reaction will take place. But if we had 4n pi electrons on the thermal conditions, we saw the reaction did not take place. So in this case, these two ethenes could not react in a one-step mechanism to produce the cyclobutane, but in this case, cyclobutane, but in this case, this reaction will take place as long as our conditions are photochemical conditions. Now, on the other hand, if we try to react our two molecules that Diels-Alder reaction under photochemical conditions, this will not take place because we have 4n plus 2 number of electrons. So we can generalize these results into the following table. So this column designates the number of electrons. So we have 4n or 4n plus 2, where n is 0, 1, 2, 3. So for example, if n is equal to 0, this becomes 0, this becomes 2. If n is equal to 1, this is 4, this is 6. If n is 2, this is 8, this is 10, and so forth. So we see that for the thermal case, if we have 4n electrons, no thermal reaction will take place. If we have 4n plus 2, a reaction will take place under thermal conditions. In the photochemical case, 4n, our reaction will take place as in this case, and 4n plus 2 as in this case, no reaction takes place under photochemical conditions.